Okay, so I believe that we are getting started here. Okay, great. So looking at it, we've got 6 attendees. Lovely to have all of you. Some of you guys I've talked to before. There might be a couple other people that are coming up. So we're only a minute away, but I'll just give a little preface here and people won't miss too much. We're going to be able to go through a PowerPoint of some information. I've included a handout in this webinar so that you can actually have that content as well. And then I'm going to be able to go through some live demonstration of the techniques using SOLIDWORKS. So I'm looking forward to sharing those things with you guys. This specifically, so this is going to be a large assemblies webinar. This is something where we are going to go over some tips and tricks first of all, and then we're going to go over how to do some error detection and how you might be able to fix some things that aren't working well. So for the large assemblies overview of the tips portion, we're going to go over sketches, parts, assemblies, and imported parts. This one seems to come up quite a bit, especially with downloads from vendors or things like McMaster-Carr models. We're going to show you how to work with those. So for a lot of this, you're going to see some similarities. Keep it simple. For sketches, this goes back to what we try to strive for as a company and as any sort of training or interacting with the customers, our internal structures as well. But you want to be accurate and fully define your sketches. Now, I was just working with something where it wasn't fully defined, and it bit me repeatedly for not doing that. And this is going to allow you to be sure that your results are consistent. If you go back into something and there's some rebuild errors, which is the next point, that's something of an identifier that this isn't okay. Certain things in your model aren't drawn well, and you're just going to continue to see those until they're fixed. That is something where that's going to be, you know, a thorn in your side that we would really like you to avoid. And we'll talk about that a little bit as well. All right, so for some of the other tips of working with sketches versus working with features, this comes up a lot with engineering and design intent. Sometimes it's down to preference. So SOLIDWORKS allows you to either work with a 2D sketch entity like a fillet, or a linear pattern or a circular pattern, or you could work with it as a 3D entity as something of a feature. For this example using with large assemblies, we're going to recommend features. The reason is going to be explained a couple different times, but features are things that you can suppress. Features are things that you could minimize or make simple for alternate configurations. That's going to come into play because when you're working with a large assembly, you might want all the detail at some point in time. Maybe you're going to manufacture a part, but do you need all the detail all the time? When you're working with a large assembly, do you need to know every filleted edge, or do you need to know, you know, all the text or different things like that? If not, with working with an assembly, maybe you're just doing interference detection, or maybe just assembly or whether or not things work well together. We're going to recommend that you put patterns into your models using features, and then your fillets, we're going to recommend that they are features as well, and we'll talk about that placement as well. So the detail inside of your sketches, you want them to be fully defined, but you don't want to strive to have every bit of detail in one sketch. That works out well for certain modeling practices. You can also reuse sketches, so that kind of defeats that, where you could use multiple features and work with what I was just talking about there with suppressing or simplifying. But if you're not used to that, then I wouldn't worry about that for now. We can teach you how to use, one sketch multiple ways. And then another thing that I've seen is that when you're choosing sketch planes, your model is going to move and change, and just to make it a lot more robust, maybe consider using the primary planes, like the front, top, and right planes, so that when things do change, if a face ID changes, then you won't have a rebuild error because the front, top, and right-hand planes are reliable. So those make your models better, which will in turn make your assemblies better. So for parts, taking those sketches, creating the 3D features, you might want to try and think in terms of symmetry. If your model has the information on one side and then it can mimic that or mirror it onto the other side, you're going to have a reduction in terms of your processing power. The file size will be smaller. The same goes for symmetrical extrusions, whether you can do that mid-plane extrusion. That's just going to be good practice. That's a good design intent modeling practice to follow by. And we'll talk a little bit about how it saves you ever so much on every little additional subtraction to your processing. Hole Wizard, if you haven't used that, we recommend that. That's actually an easy way of building in some smart functionality into your part. That also gives you the ability to alter it later, to locate it, to call it out in a drawing. There are some efficiency gains by the way they have modeled them, and we really recommend it, especially if you're working with lots of fasteners. So text, at times I've seen customers recently who have had embossed text. Reasons being is that they want to identify what you're looking at. And I totally understand that. Another way of accomplishing that same goal, if it's just a visual cue, would be just to leave it as a sketch. You'll see the sketch and you'll see the cue that you need, but you won't have the extra faces that you have to work with relative to a model and the graphical processor. Another way to do that would be to do a split line instead of embossing or actually raising the text. I will talk about that when we get to the practical example, which is shortly. So when we were talking about fillets and chamfers, those we would like to have at the end of our modeling, the modeling tree, and we're going to show you that that's going to allow you to simplify your models later. First of all, they're complex features. So if you have features that are child features to them, if you make any kind of adjustments, usually you're going to break something. So you want those at the end anyways. Anytime something's broken, it takes longer for the computer to process it. So you want things to break as least as possible, let alone the frustration that you will avoid. But the other way of maybe thinking about it, you can also start to group these with folders. So think of how the shape is really identified. That's also going to be where you want to make your mates, anything in terms of relating to other parts, and so that those secondary features, you could group those as well, and maybe you could suppress those all in one fell swoop. So that's to maybe make a simplified configuration. In full caps, no full threads. So if you're going to download a part from McMaster-Carr, it's probably going to come in as a fully threaded, so a helical cut or helical added thread. That's huge in terms of processing power that you really don't need. And we'll show a little bit of why that is. Finally, we're here at Assemblies. If you're working on an assembly with other people and your company does not have PDM, we understand that, but we recommend that you work with primarily local copies of your files. If you're going over a network, there's a lot of communication that happens between part files, between assembly files, all of SOLIDWORKS. When you're working with either assemblies or drawings, there's a lot of communication that has to go back and forth. If it has to travel over your network, it will only be as fast as your network, which is a variable that we can't control. If you're working inside of an assembly, we recommend, so I'll jump down. to the third one, group parts into sub-assemblies. So a sub-assembly is going to come in as a rigid, it almost comes in as a part. And this allows you to work with that entire group as one entity that moves together. When you're making mates for that, I would recommend mating to planes, even if it meant that you were to mate a distance or something along those lines. You can of course use the features, so circular features for axial. You can have things flush together, but try and work with those mates from a baseline. So let's say you had your original focused base or part. That would be where you are mating to. So you're either going to shoot for mating to the original planes, or you're going to mate everything to one solid foundation and object. If things are related to each other, then it becomes kind of a chain, and that chain can be broken or stretched, and that's what we want to kind of minimize. We want to have direct mates that go directly from one subassembly to maybe the main subassembly or the main component of your assembly. Flexible subassemblies are there for a purpose, but that purpose is usually temporary. That means it's going to allow you to move things and see whether or not the working operation is correct. But then once that it is finished, you should return it back to its non-flexible state, the original state that a subassembly comes into. That, even just having it in the flexible state, is using processing power. It's sitting there ready. It basically took all the mates that were inside the subassembly, brought them into the larger assembly. Every mate is a calculation. And for our demonstration, I can't wait to show you these two tools, which if you haven't used them yet, you might, after this, I hope that you're going to feel comfortable enough to use them. But assembly visualization and the performance report. Finally, if you're working with imported parts like a McMaster car, those usually are fully featured items. So that's going to be something where you would rather take the time to reduce the complexity, defeature those parts, defeature those assemblies, and reduce your graphical load, sometimes even the file size. Sometimes people say, oh, I need to get this done. I just need to get this done and working. I can go back and do that later. No, it really should be done as a first step. You should train yourself to do this before you ever work with it inside of a larger assembly. There's a lot of things that we just talked about with whether or not you're mating to original planes, whether you're using some of the object geometry. If you use this and try and fix it later, there's a lot of things that can go wrong and that mates can break. And you'll almost kind of train yourself not to use these efficiency techniques because it won't work. But that's really just not true in terms of the actual practicality of it. So because of that, let's switch over to SOLIDWORKS. Okay, so looking at SOLIDWORKS here, I've been able to gather a large assembly that's fairly complex. We have quite a few components here, maybe a piston, we've got a motor, we've got some gears, some sprockets, some wheels. Large assembly, we've got some things flexible. I told them not to, no. And then we've got some of these sub-assemblies that we could start to evaluate as well. Now, looking at this part, how would we know what is causing the most slowdown? Like, let's say that this model was starting to slow things down to a level that was unacceptable. How would we know what of this model is causing the greatest slowdown? It really comes down to these two. So assembly visualization and performance evaluation. Those two tools are what you're going to use inside of a assembly environment to get some numerical data to use to your advantage. We're going to start with performance evaluation. This is going to give you a basic readout. This is not a graphical interface. This is something where you are going to get to see Details of opening the file. This part right here that I can open directly from here, give it just a second. That file right there is taking 0.37 seconds. Again, it's going to be minuscule, but when you see how everything adds up together, that's really what we're worried about in the end. Let's see here. Close. I will just go back to that. All right, I will come back to this. The other thing that we're going to be looking for is graphical triangles. We're also going to see that in our visualization. That's a different name. So this is going to be quantity 6, total triangles, and 105,876. Graphical triangles are basically how the model is split up into triangles to show it onto your screen. The more triangles, the harder it is. Some things are going to start to get into the millions, and your graphical processor only has so much. Even the best ones only have so many graphical triangles. So we're going to have to watch out for this. The other thing that we're going to see here is image quality. 93 parts have a medium-high image quality set in document properties. 1 part have a very high image quality in the document property. So if I show these files, I get a readout, and it's going to be 1 5 zeros and an 8 4. So this one right here. I sometimes have just taken a screenshot of it. I can copy it with that. So let's say I close this. I don't know where that file lives here, but I can actually just search for it here. It'll take it quite a few seconds because it's actually starting to sort through and filter through all the different parts on here. So that's at least one way in which you can start to see how this model is sometimes affected by performance challenges. This right here is the culprit. So this is a sprocket, and this came up as a likely suspect. We should go and investigate him. I'm just going to open up him directly. You can see the design tree has some, it probably has some different configurations. Oh, it doesn't, but we have some different items that have been suppressed. But what it was specifically talking about was the image quality. And the image quality is how fine or pixelated are we going to try and make a curved surface. Flat surfaces, those are pretty easy, but how fine are we going to make this curved surface? So what we would go is go to the document properties and the model display or image quality, and we'll find our sliders over here almost maxed out into the red. And that's, see this circle that we have here? That's going to be how fine that circle is. If we put it all the way to the lowest one, we're going to have ourselves a hexagon. Not quite what we need, but look at how good this is. I think that that's a pretty good circle, and I would put maybe both of those there. And I would potentially save this, and yeah, I'll go ahead and save this one. Return back to this model, this filter cleared, and then if I were to do the performance evaluation, let's see here. Oh, he's still thinking. The filter cleared. Okay, performance evaluation, that's no longer a very high image quality. So that's something that we can get from performance evaluation. A lot of different numbers. How many parts are in this? 203. Unique part files, 87. So we've got some, you know, a couple of different instances of the same component. We could work through this, but I would like to, with the time remaining, show you something really cool. So assembly visualization, you'll see lots of pretty colors. The main, the first stop is the mass. So what is the most weighty part of this? And you'll be able to click on this, and this right here, whether it's the material that it's made out of, something like that, you can start to see what parts are the main offenders. But the mass is not going to help us with this design evaluation. We're looking for how this affects our modeling, how it affects our computer. So up here at the top, we can start to see some different options, And the one we're really going to focus right here is a performance analysis. Right here is going to be, when we click on this icon here, it's going to switch to showing the total graphics triangles, open time, and rebuild time. So you'll see that the color mapping kind of changes a little bit. It's a little tougher to see, but we saw this in the performance evaluation. Right here is our main offender. And we'll see from this that it's multiple components. So it's quantity 6 components, and then they equal the total, the largest amount of graphics triangles. If I were to click on this, I know where some of them live. They actually are these right here. You might not have guessed that originally. You might not have guessed that that's going to be your main offender, but 6 of them add up into 1, and I'm pretty sure, oh yeah, there he is. There was one up here. Okay, so why would that bearing be the main offender? Let's go ahead and open it up and take a look for ourselves. Okay, so right here we've got a nice little bearing, pretty simple layout, honestly, nothing too crazy going on here. But what possibly could be going on here on the inside? I actually have a part right here where we've got a lot of curved surfaces, some different things that are going on internally that the model also has to account for. So just because it's in a 3D assembly doesn't mean that we aren't taking into account the internal features. Okay, if you'll see this body delete right here, this is actually, it'll make a lot more sense. We've got ourselves a roller bearing where that's going on internally. The deleted feature there, that is beneficial. So if I were to suppress this, and if I were to go back to my model, this now, so this same assembly, those 6 components, just, let's see here, we're about 3.5 times what it was before. Everything else kind of pales in comparison. Actually, well, that's partly because of this and the way we have our setting. But that was not what we wanted to have happen. We wanted to reduce the complexity. So that body delete, that helps us quite a bit. So looking internally, we've got some internal surfaces, we've got some faces, but when we're working with an assembly, do we really care about all the different internal geometry? I would wager that at times you do not. That would mean that there is a place for a defeature tool. So this is going to be a tool that you normally use to take a component and reduce the complexity of that component. So it's a built-in feature. You can look for it in your command line here. And you can start to say, do you want to remove the internal bodies, things that you can't see, things that you, like those ball bearings that we didn't have. I'll say internal bodies for this. Let's see here. We're gonna have to do a couple of quick calculations. Features to keep. Well, I need to go back because, let's see here. I don't want to get rid of those middle parts because that's how we probably grabbed some of the places that it was connected to. All right, so features to keep. I want these ones here. Oh, I did too much. Well, items to remove. I was doing this yesterday. Basically, what we're gonna get to is what we would be able to simplify this model by removing some of the geometry. So some of the things like the ball bearings that we had, or whether or not we could get rid of some of the complexity of the surfaces here. I'm gonna try it one more time. I think what I was missing, features to keep, I wanna just do it this without removing the internal bodies. There we go. All right, so right here, oh, I have something else. Oh, I would need to go back and do this face and this face as well. But basically, you could get the general idea of a part. So if you download something from McMaster-Carr, you can go through the process of simplifying this part and then saving it out. When you're all finished, you could save this as a new document that's linked to the original, and you can maybe even call it the D feature. And that's right here. We'll just save that out. This one has a defeatured link here. Now you can either switch this out in terms of the component for the other one, or something really nifty that I've sometimes resulted in doing is I will set up a configuration where I will say simplified, and inside of the simplified I would insert that part into this part. So let's say I insert it there, click my green check mark. Okay, so they're sitting on top of each other, which is not what we want. We'll just go ahead and hide the other bodies. And now I've got it. Oh, actually, did I want to? Oh no, I want to do it where I don't hide it here. I hide these guys. Either way, I could suppress that or hide it. But the default, this one is suppressed. And then this one, for the simplified, where you switch to that model, you would want to have these turned off. And then when you go back to your larger assembly here, and we'll turn off the visualization. If I were to find those components, so like let's say I went to this one here, I could switch that to its simplified configuration. And you could see whether or not that would do well for your situation. That right there is going to save us some computing power for the graphics triangles. You'll see how it adjusts it for the assembly visualization. And which one, oops, we're going to go for the total graphics triangles. Now there's 5 of those components. If I were to go back and switch all of them, then they would be that much different and affected by this. So using the graphics triangles to kind of target your resources, use simplified designs to bring in models that were very complex from McMaster-Carr, whether it's internal features, whether it's going to be additional bodies that are complex with like curvatures or different things like that. You can start to walk through your model and you can see what is causing the most trouble. So these roller bearings, those would be next. Even these wheels have some complexity to them, and some of the things that you might not have even thought were going to be, things that you thought were going to be hard or looked hard, those aren't causing us nearly as much trouble as some of the simpler items. So this assembly visualization is going to give you those tools to be able to just walk through the model and simplify it one piece at a time. And as you do it, you'll see it update here. We could start to look at what are the next parts, which would be these. These are going to be the next ones. And then this was actually one thing that I wanted to take note of, is that we have one of these roller bearings. That guy is just by itself. These are all multipliers, so the 4 times the load, and that's your total graphics triangles. But this one alone, if we were to just update that one, we would reduce the graphics triangles of the entire assembly. And remember that this is total, so we're looking at everything adding up together. Quantities matter. Every single time you have an instance, that matters. It's a multiplier. and they all start to make a difference. If you make a difference at the very beginning when you're working with something that you know you're going to use multiple times, if you make sure that you have that as refined as you can. One way to do that, so stepping out of this venue here, if you want, you could just start to open up like a part from McMaster-Carr that came in. So I downloaded this pulley system from McMaster-Carr, and I did the whole situation that I showed you before, where I started off with the fully featured model. Let's see here. Looks like I have it turned off. So I had the fully featured model, and we had internal threads here. That's something that I was able to simplify out and then to resave over inside of my assembly so that I have a simplified model. But then I still have everything available so that I could use this inside of an assembly with my mates. So that's what we're encouraging. But one thing that I started doing is that I was able to do just an assembly, just a blank assembly, and I could start to drag things in here and see how they affected how many graphics triangles they had. So if I were looking, let's see here, for the simple key, if I just brought this in, I could do assembly visualization on it, and I could see that there's only 92 total graphics triangles on something like this. There's no fillets, everything's straight, everything's super good. But then if I were to insert something that I made, and I call it the stupid key. So we have embossed some text into it. We put fillets onto it, and we have gone from 92 graphics triangles to 1,496 graphics triangles. Let's say stupid key is the one that you're going to get from your vendor from McMaster-Carr, and you want to make simple key out of it. You can start with this and do a deep feature and then add it back in. That's what I did when I did the final one, which is the smarter key. So this one here, maybe I should have put baby bear in between. So I've got stupid key, smarter key, and simple key. You can start with something, and if you reduce some of the complexity, you can get it down in orders of magnitude. So this is 3 times less than this one. So just think of that in terms of fillets are not your friend for graphical triangles, because every single little part of this small curvature here, any small faces here need to be broken up into graphics triangles. This one is causing a much bigger lag on your system than this one and this one, especially this one. This one's super easy. For this one though, this one is that whole concept of going back in and changing it to be defeatured, and to make sure that I don't use embossed text. I use the split line, that's right here. I use the text, or you can just keep a sketch on that. So those are some of the keys. So performance, under the evaluate tab, so either performance evaluation or assembly visualization. This is something that we cover in our large assemblies class, but I've started to gain an even greater appreciation for it the more I see presentations about this inside of SOLIDWORKS, inside of 3D Experience World this year. Everyone wants their assemblies, especially their large ones, to work better. So simplifying, keeping it as simple as possible, recognizing that every single small face needs to be accounted for, even if it's internal. Don't just trust the things that you download from McMaster-Carr. Make sure you have a process in place where you start to evaluate whether or not you've improved the graphic triangles of the model to make sure it's no longer as horrendous to your assembly. If you can have a configuration that uses all the same mates and the faces, but basically can be brought in and is simplified, that's really something that is important to have. So I think that's a good place to pause here, and then to see if we have any questions here. I'm going to unmute the attendees, I think, and I think I did. Or people can write questions in the question tab. Give me 1 second here. Sorry, I'm checking with somebody real quick here. Okay, so I can't unmute people. So, but if you have questions, you can put them into the chat. Yeah, so Dan had a really great question. So hiding versus suppressing. So actually hiding does help the performance. It's something where it's not, so this smarter key here, let's open him up and look inside of it, and I'll use this as an example. So I suppressed the fillet, and if I were to unsuppress that fillet, we could go back into this and we could see that this is now twice as bad as what it was. So that already is something that you can see right there. Suppressing versus unsuppressing, that definitely affects your performance. So if you suppress something, does that affect the performance? The other thing that was the question is basically hide versus suppress. And that's what I was getting to with this model here, and that I didn't quite nail. So let me go back to it here, and I need to, let's see here, hide and show. Okay, so for this, I must have had a little bit hidden here, but if you can see these right here, we've got that full thread that was what I was telling you is a culprit. There's also going to be some internal features here that are real just nasty in terms of your performance. So things are showing here. I think, yeah. So for this one, I've got it now switched between. So this is the fully featured, and then I also imported back into it a defeatured model that basically represented the same thing. So if I were to go back into this assembly that I started here, I'll just use this one. And let's go ahead and insert that one component. So I'll insert, so I've got the overhead beam, and I'll do two of them. I'll do 1, 2. And one of them I'm going to switch. So for this guy, I'm going to switch to the simplified, and this is only hiding things. It's not suppressing anything. If I go back into it and I use the evaluate tool to check the assembly visualization, it's not going to completely, like this one is still, let's see here. Oh, I'd have to reevaluate the simplified to see whether or not I actually simplified it. But as you can see, the simplified has less in terms of a graphics triangle than the original model. So hiding does affect what you have and what you see and use and work with as well. Suppression is also either way. So whether you're suppressing a feature like a fillet or whether or not you're suppressing an imported solid. The thing is though, you might not want to suppress your imported solids because you might have used those for your mates, and so if you suppress it, it won't be able to be used. But if you just hide it, that actually helps your performance as well. Okay. Any other questions? Okay. Okay, well, that seems like a good place to wrap up. Really thankful for everyone's time here. Hopefully you found some of this helpful with just feeling more comfortable working with some of the tools that you have and seeing how they affect. Even though these ones are pale in comparison to something like this, they matter individually to each other, and we can show actual data to help you make your design decisions. If you have something that's a lot more complex, something like this, you can start to get a much better idea. This would be a sub-assembly in a much larger assembly. Use these tools to your benefit so that you can actually have this optimized before you even work with it and put it into an assembly. So that's what I had to share with you guys today. And I will, please reach out to us if you have any other questions. And I believe that is it.